Chapter 13 Sextants and Errors of Observation. Sextants. For hundreds of years, mariners have navigated the seas keeping track of their positions by use of the sextant. This instrument measured the altitude of celestial bodies, their angular distance above the horizon, and the information derived from this measurement was used to determine the position of the vessel. All celestial navigation follows this rule. Today's navigator measures the altitude of the celestial bodies in much the same manner as Magellan or Columbus. However, there is a difference between air and marine celestial navigation. Because marine navigators are on the surface of the ocean, they can establish their horizon by referring to the natural horizon. In an aircraft, this is impossible because altitude and aircraft attitude induce error. In the sextant designed for air navigation, a bubble like the one in a carpenter's level determines an artificial horizon, which is parallel to the celestial horizon. The bubble chamber is placed in the sextant so the bubble is superimposed upon the field of view. Both the celestial body and the bubble are viewed simultaneously, making it possible to keep the sextant level while sighting the body. Sextants are subject to certain errors that must be compensated for when determining a line of position, LOP. Some of these errors are instrument errors while others are induced by the various in-flight conditions. The first half of this chapter discusses the sextant and the second half explains sextant errors. The bubble sextant. The aircraft bubble sextant measures altitude above a horizontal plane established by a bubble. Aviators use several types of bubble sextants, all of which are indirect sighting. This means the navigator does not look directly toward the celestial body, but always looks in a horizontal direction as shown in Figure 13.1. The image of the body is reflected into the field of view when the field prism is set at the correct angle. In the bubble sextant, the bubble and body are visible in the same field of view. The Sextant System consists of 4 parts: the mount, the sextant, the electrical cables, and the carrying case. The periscopic sextant. The periscopic sextant is an optical instrument that enables the navigator to determine true azimuth, ZN, relative bearing, air bay, altitude, angle of a celestial body, and aircraft true heading, TH. The sextant provides an angle of observation from below the horizon to directly overhead, as compared to an artificial horizon. Figure 13.2, proper collimation techniques and the correct size bubble are essential ingredients of accurate celestial observations. Collimation is effected when the body is placed in the center of the bubble. For greatest accuracy, the bubble should be in the center of the field, with the body in the center of the bubble. The error is small if the bubble is anywhere on the vertical line of the field, as long as it does not touch the top or bottom of the bubble chamber. Figure 13.3 shows examples of collimation from better to worse. Bubble size affects the accuracy of a sextant observation. The ideal situation for collimation is to have a small bubble for ease in determining the center. A bubble that is too small sticks to the lens, decreasing accuracy. A bubble that is too large moves like a creature from a science fiction movie, making it difficult to find the center. Experience shows that best results are obtained with a bubble approximately 1.5 times the apparent diameter of the sun or moon, or about the size of a small watch or ring. The field prism is geared to an altitude scale so that when the body is collimated, the altitude can be read from the scale. An averaging mechanism is also incorporated that allows the navigator to take an observation over a period of time. The continuous motion of the aircraft affects the bubble and results in artificial horizon. This movement resolves itself into a cycle in which the aircraft rolls, yaws, and pitches. To obtain an accurate reading, it is necessary to sight the body for a period of time during this cyclic movement and to average the results of a series of sightings. An averaging device has been incorporated in the sextant, allowing an average reading to be obtained. The sextant is actually a low-power periscope with a 15 degrees field of view. Figure 13.4, all lens surfaces in the sextant are coated to minimize light loss. To prevent condensation when the tip of the sextant is extended into cold air, the tube is filled with a dry gas and sealed. A desiccant, composed of silica gel, is used to remove moisture and check on the dryness of the gas inside the tube and is visible in the periscopic end of the sextant, or in some models, on the sextant body. When the silica gel is pink, there is moisture in the tube and the sextant should be replaced before flight. Note, the numbers in parentheses refer to the parts indicated in Figure 13.4. An eyepiece, 1, rotates to correct the eyesight of the individual observer. Filters, 2, are provided for selective use in the optical system so that the intensity of the sun's light might be adequately reduced. The filter control, 2, is located on the left of the sextant. Most sextants currently in use have been modified with an electronic device for accomplishing all the functions of the averaging mechanism. General differences in these and the unmodified sextants are addressed in this discussion. A start switch, 4, a start and stop or averager operating lever, 4A, on unmodified sextants, starts and stops the operation of the sextant. Adjacent to this switch is the reset switch, 5, the average or rewind lever, if unmodified, 5A, located below the average or operating lever. The reset switch, or average or rewind lever, has 4 functions. When depressed and released, it does the following: 1. Removes the shutter from the field of vision. 2. Zeros and resets, rewinds if unmodified, the timer. 3. Zeros the averager and places initial values in registers in data memory, realigns indices on unmodified sextants, and 4. Disconnects the altitude control knob from the averager. The bubble control knob, 6, should be left in the maximum increase position after adjustments have been made. With a control in the maximum increase position, an aneroid is locked to the bubble chamber to compensate for changes in ambient pressure and temperature. On the front of the sextant, there is a rheostat control, 7, that varies the intensity of the light in the bubble chamber. The altitude knob, 8, is located on the right side of the sextant. It keeps the observed body in vertical collimation during the period of the observation. At the end of the scheduled observation, it adjusts the altitude counter until the exact average indication appears, or to align the indices on unmodified sextants. The body's altitude is read in the altitude counter, 9. Directly behind the altitude knob is the averager display, 10, half-time dial and indices if unmodified. The averager display, or half-time dial, is graduated from 0 to 60 and indicates the half-time of the observation. The indices, when aligned, permit the direct reading of the observed altitude on the altitude dial. In the periscope sextant, the averaging is accomplished by microprocessor, email blackball integrator if unmodified, which effects a continuous moving averager over any observation period up to 2 minutes. This system is very simple to operate and has many advantages over other known averaging devices. A single switch, or lever, sets or winds the mechanism and no other presetting of the sextant, timing mechanism, or averaging is necessary. It is continuously integrating altitude against elapsed time. After at least 30 seconds, it may be stopped at any time up to 2 minutes. The average altitude is read directly from the counter. A halftime clock indicates the halftime of the observation. The time indication may be added directly to the time of starting the observation to compute the mean time of the observation. At the end of the observation, the averager energizes a solenoid. Actuates a lever if unmodified, that drops a shutter across the field of view, indicating the end of the observation. Although it is possible to utilize an instantaneous shot, the normal timed observation lasts for 2 minutes. It is impossible to time any observation for less than 30 seconds using the sextant timer. A heading scale shutter, diffuser lever, control, 11 provides a convenient means of blocking out the bright illumination on the azimuth scale for night celestial observations. The objective lens, 12, is located just above the heading scale shutter control. The lens aligns the azimuth scale of the sextant with the longitudinal axis of the aircraft. The lens can be rotated with the fingers in order to calibrate the azimuth scale on a known bearing while looking through the eyepiece. The objective's lens can remove up to 2 degrees azimuth error in the azimuth ring. A locking ring beneath the lens prevents accidental movement. A dial lamp located on the right side of the sextant provides 3 beams of light to illuminate the averager indicators, the altitude counter, and the watch clip. The watch clip is made to hold an old-fashioned pocket watch. Electrical cables provide power for sextant operation and illumination. 1Y cable provides power from the mount to the sextant for illumination and averager operation. Sexton Case. The case provides shock-absorbent storage for the sextant when it is not in use. The sextant fits into form-fitting foam blocks and is secured by straps. The case also contains spare bulbs for sextant illumination and provides storage for the electrical cable. Errors of sextant observation. If collimation of the body with the bubble and reading the sextant were all that had to be done, celestial navigation would be simple. This would mean LOPs that are accurate to within 1 or 2 miles could be obtained without any further effort. Unfortunately, considerable errors are encountered in every sextant observation made from an aircraft. A thorough understanding of the cause and magnitude of these errors, as well as the proper application of corrections to either computed altitude, HC, or H's, helps minimize their effects. Remember that any correction applied to the H's may be applied to the HC with a reverse sign. Accuracy of celestial navigation depends upon thorough application of these corrections, together with proper shooting techniques. The errors of sextant observation may be classified into 4 groups: parallax, refraction, acceleration, and instrument. Parallax error. Parallax in altitude is the difference between the altitude of a body above a bubble horizon at the surface of the Earth and its calculated altitude above the celestial horizon at the center of the Earth. All HC are given for the center of the Earth. If the light rays reaching the Earth from a celestial body are parallel, the body has the same altitude at both the center and the surface of the Earth. For most celestial bodies, Parallax is negligible for purposes of navigation. Parallax correction for the moon is so close to the Earth that its light rays are not parallel. The parallax of the moon may be as great as 1 degree, thus, when observing the moon, a parallax correction must be applied to the H's. This correction is always positive, plus, and varies with the altitude and with the distance of the moon from the Earth. The correction varies from day to day because the distance of the moon from the Earth varies. Corrections for the moon's parallax and altitude are given on the daily pages of the Error Almanac and are always added, algebraically, to sextant altitudes. The values of parallax for negative altitudes are obtained from the Error Almanac for the equivalent positive altitudes. Semidiameter correction is found on the daily pages of the Error Almanac. Apply it when shooting the upper or lower limb of the moon or the sun. It is more likely to occur on observations of the moon because, when the moon is not full, completely round, the center is difficult to estimate. Shoot either the upper or lower limb and apply the semidiameter correction listed on the Error Almanac page for the time and date of the observation. Subtract the correction from the H's when shooting the upper limb, add the correction to the H's when shooting the lower limb. Reverse the sign if applying the correction to the HC. Listed on the same page is the semidiameter correction for the sun, which is applied the same way as for the moon. Example, using figure 13.5, extract the corrections for the upper limb of the moon as observed on August 11, 1995 at 1100 Z as 33 degrees 41. Apply these corrections as, H is 33 degrees 41 parallax plus 49 semidiameter minus 16 Ho 34 degrees 14 atmospheric refraction error. Still another factor to be taken into consideration is atmospheric refraction. If a fishing pole is partly submerged underwater, it appears to bend at the surface. The bending of light rays as they pass from the water into the air causes this appearance. This bending of the light rays, as they pass from one medium into another, is called refraction. The refraction of light from a celestial body as it passes through the atmosphere causes an error in sextant observation. As the light of a celestial body passes from the almost perfect vacuum of outer space into the atmosphere, it is refracted as shown in figure 13.6, so that the body appears a little higher above the horizon than it really is. Therefore, the correction to the H's for refraction is always negative. The higher the body above the horizon, the smaller the amount of refraction and, consequently, the smaller the refraction correction. Moreover, the greater the altitude of the aircraft, the less dense the layer of atmosphere between the body and the observer, hence, the less the refraction. The appropriate correction table for atmospheric refraction is listed inside the back cover of all 4 books used for celestial computations, namely, the Error Almanac and each of the 3 volumes of publication No. 249. It contains the sight reduction tables for air navigation published in 3 volumes. Volume 1, used by both the Marine and Air Navigator, contains the altitude and azimuth values of 7 selected stars for the complete ranges of latitude and hour angle of Aries. These 7 stars represent the best selection for observation at any given position and time, and provide the data for presetting instruments before observation and for sight reduction afterwards. Volumes 2 and 3 cover latitudes 0 to 40 and 39 to 89, respectively, and are primarily used by the Air Navigator in conjunction with observations of celestial bodies to calculate the geographic position of the observer. This table, shown in figure 13.7, lists the refraction for different observed altitudes of the body and for different heights of the observer above sea level. The values shown are subtracted from H's or added to HC. Acceleration error. Presently, the only practical and continuously available reference datum for the definition of the true vertical is the direction of the gravitational field of the Earth. Definition of this vertical establishes the artificial horizon. It is also fundamental that the forces caused by gravity cannot be separated by those caused by accelerations within the sextant. A level or centered bubble in the sextant indicates the true vertical only when the instrument is at rest or moving at a constant velocity in a straight line. Any outside force, changes in G's or changes in track, affect the liquid in the bubble chamber and, consequently, displace the bubble. When the sextant is moved in a curved path, Coriolis, changes in heading, rhumb line, etc., or with varying speed, the zenith indicated by the bubble is displaced from the true vertical. This presents a false artificial horizon above which the altitude of the celestial body is measured. Since the horizon used is false, the altitude measured from it is erroneous. Therefore, the accuracy of celestial observations is directly related to changes in track and speed of the aircraft. Acceleration errors have 2 principal causes: changes in G's and curvature of the aircraft's path in space. The displacement of the liquid in the bubble in the chamber may be divided into 2 vectors, and each vector may be considered separately. These vectors may be thought of as a lateral vector, along the wings, and a longitudinal vector, along the nose-tail axis of the aircraft. Any change in g's can cause a longitudinal displacement. This change can be brought about by a change in the airspeed or the wind encountered, or the change in g's brought about by a change in heading due to other factors, gyro precession and rhumb line error. A lateral displacement results from a number of causes, most of which occur in spite of any efforts to hold them in check. These causes are Coriolis, rhumb line, and wander errors. Coriolis force: any free-moving body traveling at a constant speed above the Earth is subject to an apparent force that deflects its path to the right in the northern hemisphere and to the left in the southern hemisphere. This apparent force, and the resulting acceleration, were first discovered shortly before the middle of the 19th century by Gaspar Gustave de Coriolis, 1792–1843, and given quantitative formulation by William Ferrel, 1817–1891. The acceleration is known as Coriolis acceleration, or force, or simply Coriolis, and is expressed in Ferrel's law. You must realize that the bubble sextant indicates the true vertical only when the instrument is at rest or moving at a constant speed and a straight line is perceived in space. If the Earth were motionless, this straight path in space would also be a straight path over the surface of the Earth. Conversely, a straight path over the motionless Earth would also be a straight path in space. When the aircraft is flying a path curved in space to the left, the fluid in the bubble chamber is deflected to the right, and the bubble is deflected to the left of the aircraft's path over the Earth. When the aircraft is flying a curved path in space to the right, the reverse is true. In Figure 13.8, the aircraft is represented as flying on a curved path to the left. Note that in the inset representing the bubble chamber, the heavy black bubble is indicated in its approximate position representing the true vertical. The observer always seeks to center the bubble and, on this beam shot facing to the right side of the aircraft to observe the body, tip the sextant up. This would tilt the bubble horizon from its true position, producing a smaller sextant reading than the true value. The smaller the height observed, the greater the radius of the circle of equal altitude, the lop falls farther from the subpoint than the true lop. Obviously, if the erroneous lop falls farther from the subpoint, it falls to the left of the true lop and the correction to the right is valid. Corrections for Coriolis error are shown on the inside back cover of the Error Almanac, as well as in all volumes of Pub. No. 249 published by the National Imagery and Mapping Agency. Coriolis acceleration is directly proportional to the straight line velocity, directly proportional to the angular velocity of the Earth, directly proportional to the sine of the latitude, and at right angles to the direction of flight. Rhumb line error: the straight Coriolis table in Figure 13.9, found in the Error Almanac or Pub. No. 249, has a limited application. As long as a constant th is flown, the path of the aircraft is a rhumb line. Because a rhumb line on the Earth's surface is a curve, it is also a curved line in space. If the aircraft is headed in an easterly direction in the northern hemisphere, the apparent curve is to the left and becomes an addition to the Coriolis error. By the same token, if headed in a westerly direction in the northern hemisphere, the apparent curve is to the right, or opposite that of Coriolis force. Figure 13.10, there are notable exceptions to this. When flying north or south, the aircraft is flying a great circle and there is no rhumb line error. Also, when steering by a freerunning, compensated gyro, the track approximates a great circle and eliminates rhumb line error. At speeds under 300 knots, the error is negligible. However, at high speeds or high latitudes, rhumb line error is appreciable. For example, at 60 degrees north latitude with a track of 100 degrees and a Gs of 650 knots, the Coriolis correction is 15 nautical miles, nm, right, and the rhumb line correction is 10 nautical miles right. Use the following steps in Figure 13.11 to determine the correction for rhumb line error and Coriolis correction. 1. Enter the nearest latitude on the left side. Interpolate if necessary. 2. Enter the nearest track across the top of the chart. Interpolate if necessary. 3. Choose the closest Gs and extract the correction. 50 N, track 080 degrees, Gs 500 knots equals 14.3 right. Ground speed acceleration error: changes in airspeed or wind velocity cause this error. Prevent changes of airspeed through good crew coordination. Changes in wind velocity with resultant changes in Gs are more difficult to control. The change in Gs causes the liquid to be displaced, with the subsequent shifting of the bubble creating a false horizon. Notice in Figure 13.12 how the horizon is automatically displaced by keeping the bubble in the center while these changes are taking place. A very simple rule applies to acceleration and deceleration forces. If the aircraft accelerates while a celestial observation is in progress, the resultant lop falls ahead of the actual position. Accelerate, ahead. The more the lop approaches a speed line, the greater the acceleration error becomes. Refer to Figure 1313. 1. Enter with ZN track. 2. Extract acceleration error and apply sign. Example, track equals 080 degrees, ZN equals 060 degrees, beginning Gs minus 500 knots, ending Gs minus 515 knots. 060 degrees dash 080 degrees equals 340 degrees equals minus 1.40 515 to 500 equals 15 knots minus 1.40 times 15 equals minus 21. Correction to the HO. Wander error. A change in track can be produced by changes in the wind, heading changes caused by the autopilot, changing magnetic variation, or by heading changes caused by pilot manual steering errors. As with the Coriolis force and run line errors, correction tables have been developed for wander error. Values extracted from the wander correction table, shown in Figure 1314, are to be applied to the HO. Use the following information as entering arguments for the determination of the correction taken from the table. 1. The heading at the beginning of the observation was 079 degrees. 2. The heading at the end of the observation was 081 degrees. 3. The observation was taken over a 2-minute period. 4. The Gs was 450 knots. 5. The Zn of the body was 130 degrees. Following the instructions shown at the bottom of the table, enter the numerical portion of the table with the values of Gs and the change of track per 2 minutes. In this case, the Gs is 450 knots and the change in track per 2 minutes is 2 degrees. Since the heading at the end of the observation is greater than the heading at the beginning, the change is 2 degrees to the right. Notice that you must know whether the change is to the right or to the left to determine the sign of the correction. The factor obtained from the table is 12 times 2 equals 24. Next, enter the graph portion of the table with the value of the factor, 24, and the value of the azimuth of the body, minus the value of track. The graph is so constructed that it must be entered with ZN-TR. ZN-TR equals 130 degrees, 080 degrees, so use 050 degrees following the rules in steps 2 and 3 in the table. The correction is 19. Since the change in track is to the right, the correction is subtracted from the HO. This is determined by referring to the signs shown at the ends of the arc in the table. Figure 1315 shows the effect of this correction. If the track and ground speed are the same at the beginning and the end of a shooting period, there is no wander error. Instrument error. Index error is usually the largest mechanical error in the sextant. This error is caused by improper alignment of the index prism with the altitude counter. No matter how carefully a sextant is handled, it is likely to have some index error. If the error is small, the sextant need not be readjusted. Each H's can be corrected by the amount of the error. This means that the index error of the sextant must be known to obtain an accurate celestial lob. Another mechanical error found in sextants is backlash. This is caused by excessive play in the gear train connecting the index prism to the altitude counter. Usually, index and backlash errors are nearly constant through the altitude range of the sextant. Therefore, if the error at one altitude setting is determined, the correction can be applied to any H's or HC. The correction is of equal value to the error, but the opposite sign. The sextant should be checked on the ground before every celestial flight. Pre-flighting the sextant can determine the sextant error of an individual instrument. The sextant error can also be determined in flight and a correction can be applied to the pre-comp to compensate for the error. To determine the error and correction in flight, one must have a celestial lob, a ZN, and the actual, or best known, position of the aircraft at the same time. Figure 1316. The fixed symbol represents the best known position at the time of the celestial lob. To determine the actual value of the correction, measure the shortest distance between the position and the lob. This tells you how many minutes of arc, nm, the HO must be adjusted on subsequent shots to get an accurate lob. In this case, the value is 10. To determine whether this value must be added or subtracted, note whether the lob needs to be adjusted toward the ZN or away from the ZN. Remember the rule Homodo. It applies here too. If the lob needs to be moved toward the ZN in order to be made more accurate, the HO needs to be made larger, thus, the correction is added to the HO to make the HO value increase. If the lob needs to be moved away from the ZN, the correction is subtracted from the HO to make the HO less. In Figure 1316, the lob needs to be moved 10 miles toward the ZN in order to be accurate, thus, the sextant error correction is plus 10 to the HO and can be used on subsequent shots obtained from the same sextant. An important thing to remember is that the sextant error correction assumes conditions are consistent. As a technique, it is wise to obtain several lobs with a sextant, noting the sextant errors on each, before establishing a value to be carried on the pre-comp. Once using that correction, make sure you use the same sextant. Chapter summary. The first half of this chapter describes the parts and operation of the sextant, and the second half explains sextant errors. Remember to apply parallax, semi-diameter, and refraction errors on every applicable shot. Corrections for acceleration errors can be applied only if you know the track and ground speed before and after each shot, so be aware of your speed and direction when shooting. Time permitting, always try to evaluate the accuracy of your sextant on the ground.